Major concepts in MapReduce processing sits on top of a distributed file system in either Google file system, the Hadoop file system, or it could be Lustre, it could be some kind of distributed file system. The basic concept is programs are sent to the machines or nodes that have data and process the data locally where it resides, called the map step. The output of the local processing is retrieved and shuffled and resorted, basically, and sent back to nodes so that the output is now sorted on some primary key, and each node has some subset of those primary keys. So underneath all this, and then you run a reduce program on the reorganized data, add it up, average it, do some kind of reduction process. And you may do this several steps, several times, and repeat it. For instance, PageRank is an iterative process. They run this 10, 15 times to compute page ranks across all of their web pages. But if underneath it, MapReduce becomes a massive sort, merge, and processing infrastructure, capable of scaling to petabytes of data. Some of the big clusters now have 30,000 nodes in them, with the data spread across all these 30,000 cores and maybe 10,000 servers or 5,000 servers, each one having at least a moderate amount of disk on it. So we need to talk about the MapReduce processing model, because this is one of the key elements of this new technology. It's based on functional programming concepts. For those of you who are in computer science, you probably know what functional programs are, like Lisp and things like that, where basically we're sending functions to operate on data. And an associated implementation for processing and generating these large data sets. So the way the processing goes is the user specifies some kind of map function that processes a key value pair of the input and generates a set of intermediate key value pairs that are implicitly reorganized and sorted, and then these are distributed back to different nodes, and then a reduce function is sent to the nodes that now have this shuffled or sorted data, and that merges all the intermediate values associated with the same intermediate key, processes them down. Turns out that you can do a lot of damage with this kind of processing model. For those of you who've been around a long time, this is back to sort merge processing, but almost back to thinking sequential processing on tapes. This is the kind of thing we used to do. Very good for things like computing page ranks, Google Analytics. Lots of Google's products are built on top of this. And the nice thing here is that programmers just specify what they want done, not how to do it. The infrastructure handles all the details and parallelizes things across as many systems as there are available. And you can just add more processing power, more disk storage to this, and it scales literally, maybe not quite forever, but pretty far. So the MapReduce processing system really was designed to handle batch kinds of processing, where you want to pass most of a data set sequentially and do something to it, summarize it, add it up, pull out strings, build an inverted index, different kinds of operations. And Google and now Yahoo and Facebook and many of these companies use MapReduce to do a lot of their processing. And now many common algorithms have been redesigned so they can be processed using MapReduce kinds of systems and made implicitly parallel, and the programmers don't have to think about the parallelism. The Hadoop project, which we're going to talk about in a few minutes, has extended this and added some higher level tools, including Pig, developed at Yahoo, which is a high-level language that users can express their processing requirements in, and it compiles to MapReduce programs. Mahout, Mahout is, by the way, Hadoop is the name of the toy elephant of the guy who developed the Hadoop project. And Mahout, if you know, is the trainer or driver of an elephant. So Mahout, the Mahout project is a data mining project that can handle really very large data sets. And it, again, generates a sequence of MapReduce jobs automatically to do naive Bayes, cluster analysis, neural networks, different kinds of data mining kinds of algorithms. There's also Pegasus, which is a new project similar to Mahout, but it's designed to handle the large network graph data sets that you see, that you get in web data, where you have graph networks with millions of nodes that you want to analyze. You can't fit them in memory, and there's no way to do it except sequentially and with big files. So the process is the map step takes input, generates key value pairs. The shuffle step then rearranges the data so the keys are together, contiguous anyway, sort of an implicit semi-sort. Then you run something across the reordered data and summarize it in some way. And you may have to do this multiple times. So the user just specifies the mapper program or writes the mapper program. In some cases, the mapper program can be as simple as awk and grep and things like that in the Unix LAN, as well as the reducer program. And the system does everything else. So let's go back for a second and talk about Hadoop and where it came from. Back in about 2005, a guy named Doug Cutting started the Hadoop project to see if he could replicate the Google file system approach and MapReduce. And he named the project after his child's toy elephant. And so he used open source tools, Java in particular, to build a replica of the Google file system called the Hadoop file system and MapReduce. And the projects picked up a fair amount of support. It was sort of interesting because Google had a proprietary architecture, and this was now basically open sourcing their approach. Yahoo in 2007 had been having terrible problems handling the amounts of search engine data they were generating. And they looked at this Hadoop project and said, we're going to give up and hire Doug Cutting and see if we can put some muscle behind this project. They did, and in 2008, Hadoop, running on a 10,000 core Linux cluster at Yahoo, set the world sorting record. So that was pretty fast. In 2009, Yahoo turned around and contributed its code code base to open source it as an Apache project, to open it up to lots and lots of developers. Somewhere in that timeline, Facebook jumped on because they were having similar problems. They'd started with a MySQL infrastructure that wasn't scaling. And they started adding a bunch of other things to Hadoop and picked up Hadoop. And in 2011, they announced that they had the world's largest Hadoop cluster that had 21 petabytes of storage. I think it's now closer to 30 or 40 petabytes of storage. In the last year, Hadoop has been adopted by major vendors, IBM, EMC, Oracle, and many others, to either front-end their old relational databases or to come up with Hadoop out-of-a-box kinds of processing systems. So Hadoop has now become the standard infrastructure at big data companies and a major tool for data scientists who are trying to deal with very, very large data sets. So here's an example, a very simple example of a MapReduce program. This is the example that, sort of the starter example that everybody uses. And the idea is to count the words in document or text corpus by word. So I want to know how many occurrences of each word occurred in some set of documents. And the map step is trivial. You go through the set of documents, and for each word in the documents, you put out the word followed by the number 1. So you have a file that has, for each word, the number 1 following it, for each occurrence of each word. The reduce step is very simple. It goes through, because remember now the reduce step is going to see that output from the mapper in sorted order. So all the reduce step does is iterate across all the words and add up the number 1s to come up with the word and how many times it occurred across the whole set of documents. Notice the program is virtually trivial. The map program is trivial. The reduce program is trivial. But you can run this program on a cluster of 10,000 machines and add up and produce a word count on an enormously large corpus of text. So here's an example of what the output of the map step would look like. Word 1, number 1, word 2, number 1, word 3, number 1, word 1, number 1, word 2, number 1, etc. Then the output of what's presented to the reduce step is word 1, 1, word 1, 1, word 2, 1, 1, word 2, 1, word 3, 1, etc. And the reduce step just adds up the value for each key and put outputs for word 1 that occurred twice, word 2 occurred twice, word 3 occurred once. Boom. Can do that for a very large set of data very, very quickly. Some other examples. Let's say I want to find out what keyword is in what web page. I can take a list of HTML documents and generate the keyword and the URL that it appears in. So instead of the 1, I'm now doing the URL. And the reduce step, remember again that this is going to be sorted by keyword. So now I have the keyword followed by the list of URLs that contain it. Well, that's an inverted list. I can then find out what, if I know, say the keyword is HPC is one of them and NYU is another one of the keywords, I can find out which URLs contain both HPC and NYU by just retrieving the two lists. This goes back to a project at IBM, the project called Storage Acquisition and Information Retrieval that IBM did in the late 60s, coming up with inverted lists like this. So the programs written in this functional style automatically parallelized and executed on this large cluster. The runtime system takes care of all the details, including handling machine failures, because some of these jobs might run for a day, a week, for some of the big ones, and the probability that in a cluster of 10,000 machines that something's going to happen is virtually 1. So the whole infrastructure is designed to transparently handle and recover from errors of major types. It typically scales close to linearly with the number of nodes, at least in the range of up to 10 or 20,000 nodes. So you can really attack very, very large problems with a lot of relatively inexpensive hardware, actually. These are not typically HPC class types of hardware. Some other examples, distributed grep. I want to find all lines in a text corpus that that contain some pattern, right? Well, this could be done in a totally distributed fashion, and you can do this very, very quickly. You can search huge corpuses to find out what kinds of things, what lines contained what words. The count of the URL access frequency in a web log, similar to the word count. Just look at the web page logs and output a line that contains URL, 1 for each URL, and send it to the reduce step, just adds them up, and now you've got how many hits you're getting by each web page on your website. Inverted index of web page, I've already described how you would do that just in the previous slide. Distributed sort, since the Hadoop infrastructure and the Google infrastructure, MapReduce infrastructure, sorts implicitly, all you do is have a map step that produces the key and the record, and the reduce step automatically sorts it. As long as you come down to one reduce step, all the pairs are sorted and you're done. So sorting large amounts of data is trivial. So how does this all fit together? Well, the system has what's called a master scheduling machine. In Hadoop world, that's called the Hadoop name node. And it knows what nodes get what data. It controls replication. It has the file system that knows where the pieces of a file are stored. It's basically the meta store of the file system. And it, by the way, is a single point of failure. If the name node goes down, the whole thing stops. But you don't lose any data, as we'll see in a minute. Then you have many, many chunk servers. These are the nodes, and data is chopped into fixed size chunks, 64 megabytes, 128 megabytes. Depends how big your files are and what your problem is. And distributed to the chunk server nodes. Default is 3 replicas, but you can run with 1 or 10 or whatever the user wants. The client servers request data from the master machine, which in turn tells the chunk servers where to send it. So if I want to get a particular data block, I ask the master client, where is it? And it then tells the correct chunk server to send it to me. So underneath all this, there is a high-speed network interconnecting all of the nodes together, because they really talk back and forth to each other, with the master scheduler just telling machine X to send program and or data to machine Y and process it. So the new model here is, hey, we have this distributed file system. Let's send the program to the chunk server that has the data on it, and let each chunk server process the data that they have, rather than moving the data around. The data movement is only when the shuffle step has to move the intermediate output to different nodes. As we'll see, there's some tricks you can do. It's called a combine step. So in the word count example, I can run a reduction step on each node before I send the data back to be sorted, and that dramatically reduces the amount of data movement. So there's some tricks you can do. Whole system is fault tolerant. Because it's a functional programming model, these programs are all independent of each other. If a machine dies or doesn't respond, the master node knows what it was supposed to be doing, and it just sends that program to another machine that has the same data and tells it to process there. And by the way, it also immediately notices that block is not doesn't have enough replicas, and finds a block and copies that block someplace else. So it keeps the replication factor up. Very robust. One example, Google was doing some long weekend run. This is early days of Google, and they had 1,800 machines in their cluster. And I don't know what happened, a switch died or something, but 1,600 of the 1,800 machines went offline. However, there were enough replicas that no data was lost. The MapReduce jobs kept going, although albeit much more slowly, because they'd lost most of their capacity, but the job still finished, just a little bit more slowly, or a lot more slowly. And you can do some wrinkles on this. Hadoop and Google use what they call redundant execution. Unlike HPC, you do not have to have homogeneous nodes here. These nodes can be of far differing capacities and speeds. So that some nodes could be very slow, some nodes could be very fast. The faster nodes just get more work. The slower nodes go slower. But sometimes some nodes might get really, really slow. Maybe you're getting an intermittent disk hit or something. Well, as the job starts to finish, the scheduler is going to look around and say, that node 43 is really not gone slowly. I'm going to pick up the work that's on node 43 and send it to node 57. And whichever one finishes first, we're going to use those results, because the results are going to be the same. Turns out this can dramatically shorten job completion times in very large clusters, where typically some machines are having a problem, they're going offline, their cache is dead, and all sorts of things could happen to them. Actually, I've already talked a little bit about the Hadoop project, but after the Hadoop project started at Yahoo, there were a number of related projects that were built on top of both the Hadoop file system and the MapReduce processing system. And these are Hive, which is a data warehouse solution, HBase, which is a highly scalable distributed data storage system, Mahout, data mining, Pegasus, I've talked about, the graph network analysis, Cassandra, which is another high-speed data storage and retrieval system, and Pig, which I haven't mentioned yet, this high-level system for analyzing extremely large data sets. It's named Pig because it can eat anything. You sign into Pig and your prompt is grunt. Heavily used at Yahoo and Facebook to do their data analytics, or parts of their data analytics are done in Pig. So the current status is that the Hadoop project is now, in fact, I think they just released the first real 1.0 release of Hadoop and HBase, used by many, many, many companies, especially in the new media field, search companies and the like. And this whole approach has now been sort of named big data and no SQL for these Hadoop-like approaches. There are some other systems out there like MongoDB that have distributed sharded databases that are also similar. used by the back end for many startups. I mean, Instagram just went public for $1 billion, just was bought by Facebook for $1 billion. And Instagram had a Hadoop back end, and they, if you read the story, they had to add like 300 servers over a weekend on Amazon EC2 when they started to really take off. Given here a list of Hadoop sites for you. That list changes every day, but it's sort of like the top 500 HPC sites. You can go and see who's using Hadoop today for what. My takeaway here is that Google and now Hadoop have generated this whole new infrastructure that really can be used for lots and lots of different kinds of commonly occurring problems, not just in the search field, but also in scientific computing, in social, in all sorts of research and education. I've gone through here and just done a little research, and for Todd, for instance, here's bioinformatics. I'm sure he's heard of some of these things, but there's apparently a lot of work in bioinformatics of distributing some of the bioinformatics algorithms across Hadoop clusters. There's a My Hadoop project at the San Diego supercomputing cluster, which is one of the many attempts or approaches as how do you take an existing HPC cluster and plop Hadoop on top of it so that you can use Hadoop to attack problems that are not massively parallel kinds of problems. There's another experiment, a number of experiments actually going on with Hadoop, using Lustre instead of HDFS for the underlying file system. Because if you think about it, if you have a flat file system like Lustre with 40 gigabit network links, you don't have to do that data shuffling. There's some tricks that you can do and just sort of remap where the data is so the nodes can start processing their data and getting it directly from Lustre without it actually being moved from one system to another. And then one of the latest things is what happens if the Hadoop nodes also have GPUs? And it turns out there's a lot of articles on this, which again takes which takes typical HPC clusters that have Hadoop have GPUs in them, and can use these GPUs for processing. Turns out in that environment you don't need anywhere near as many nodes, especially if your jobs are CPU intensive. Hadoop and MapReduce have been used for surface temperature modeling. I reference a paper there. And the CUSP project, which is just starting, and we're about to have the new director of CUSP named within a couple of days, is a smart city project. And smart cities will be generating lots and lots of data that are going to need Hadoop-like technologies to process it. So my takeaway here is that these big data approaches are applicable to many types of university research projects, including both the social sciences and the hard sciences. Our students need some big data exposure. The jobs are absolutely exploding for people with big data experience, and there are very few people out there. I can talk about that maybe next fall. We've done some research there. Existing HPC installations can actually easily accommodate big data software and applications with good performance. In fact, I think Sheng over at the NYU HPC cluster already experimented a little bit with running Hadoop on top of it. But the bottom line is I think NYU needs a plan for big data. We need a university-wide look at big data, and not just what it can do for the hard scientific research, but curriculum, training, education, research in the soft sciences, social sciences, whatever. Well, that's the end of my presentation. I'd be glad to talk about this next fall at our first meeting and see what people think. Thank you very much.